So first of all, so thank you very much for being here, Yuying. It's early in the morning in Canada.
Yes.
Yuying Li is professor at the Cheriton School of Computer Science at the University of Waterloo. She's very well known for optimization methodologies and already worked on machine learning, more than a decade ago, I would say, right? So really very senior in data science and financial data science. And she works on supervised learning and unsupervised learning, on anomaly detection, fraud detection, data-driven optimal decisions, computational finance, and computational optimization. She's an associate editor of several journals, and at present she's also the director of data science at the University of Waterloo. So it's a pleasure to have you here, Yuying. And you will be talking in our second keynote on asset allocation without pain, learning dynamic strategies directly from market data. So
thank you very much, Case. Thank you.
Let's see if the screen sharing works. And then, so Swai Cheng's screen, Swai Cheng can maybe stop sharing the screen. Right. So Swai Cheng, can you stop sharing your screen? And then it's Yuying. So as soon as the screen sharing, yes, that works out fine. So the floor is yours, Yuying.
Yes, just give me 1 second to set it up. Okay, I have to do it again, sorry. Share it again. Oops.
Yes.
Okay, now it works. Okay.
It works perfectly. The floor is yours.
Well, thank you again, Case, and the workshop organizers to invite me to be participating in this session. So in this presentation, I would like to talk about some recent research that have been conducted here with my colleague. So this is a joint work with a PhD student, Yuying Li, and my colleague, Peter Forsyth, both at Waterloo, and also Ray Carroll at a asset management firm in asset management firm Neuberger in Toronto. My colleague Peter always liked to say that he liked to quote Frosenberg from who is the previous managing director of Morgan Stanley. Every financial application problem is a stochastic optimal control problem. So certainly optimal control problems is an important class of financial application problems. So in this talk, I would like to talk about how we can learn optimal control of particular dynamic asset allocation strategies directed from the market data. Okay, so here's the outline of my presentation. So I will begin with introducing the mathematical formulation of the optimal dynamic asset allocation problem. And the focus of my presentation are particularly for problems that is involving many times rebalancing, long time horizon allocation problem. And I will talk about what is the traditional approach of solving this problem, what are the challenges. And most of my presentation, I will use a particular application problem that is the pension allocation problem as an illustration to the proposed framework. As well, I will talk about our empirical assessment in performance strategy based on that pension allocation problem. So then I'll move on to talk about what is the approach we propose to solve this class of problem that is different from the traditional approach. And in essence, we're going to take a direct learning approach from the market data to determine the optimal allocation problem. And so I will talk about how specifically we perform learning how specifically we do the learning. I will talk about what are the data that we will use to actually solve our learning problem, and we will use a nonparametric approach to augment the observation from the financial market. And then I'll talk about how we actually learn, because this is a multi-stage and optimal dynamic control problem. And we will propose to solve the problem by solving a single training optimization for all the multiple steps optimal control using a neural network. I'll talk about the advantage of solving problem in this fashion. And then particular to the specific application of pension asset allocation, I will describe different possibility of objective function that can be used to generate attractive allocation strategies. And I will talk about how objective function corresponds to reaching a constant level of wealth level at the retirement time, or actually getting a strategy to outperform a benchmark strategy that's used in industry. And so then I will present the computational results based on real market data in terms of the accuracy of the optimal strategy we can compute, and robustness, as well as the characteristics of the dynamic pension allocation strategy themselves. Then I will conclude my presentation. All right, so mathematically, basically we're looking at that today. We want to determine dynamic optimal trading strategies or allocation strategies, which rebalance at a regular interval, for example, every year, possibly for a long time horizon, let's say 30 years from now. And today's time, the future return are random. So we have a vector of M assets, and the return per each period is a random vector RTN. Okay, and in my presentation, I will also focus on the situation. We have some control, some constraints on the control. In particular, we'll assume that no shorting is allowed, no leverage is allowed. Okay, and we will in the formulation, I'm going to also assume that our assessment, performance assessment of the strategy is based on the terminal wealth at the end of allocation time horizon. So then we can write mathematically this optimal dynamic control problem as I'm going to minimize some objective involve the random terminal wealth WT. Subject to my optimal control will be, here I'm looking at percentage allocation, so the optimal control will be between 0 and 1, and they will sum to 1. Okay, so this mathematical formulation, this mathematical optimal control problem, it's a difficult optimization problem. In fact, that it's in terms of optimization, I can think of it as a infinite dimension optimization problem, in the sense that my optimal control at each rebalancing time itself, they are functions, and they depend on the random realization of your market scenario. So in any case, this is the framework of the problem I wanted to solve. So as I mentioned, that I will use the pension investment as a particular example of such dynamic allocation problem. And indeed, this problem by itself is very important because that in North America and all over the world, it's increasingly recognized that there's a risk of a pension funding shortfall. And in North America, there is a large shift for pensions to go from defined benefits to defined contribution. And this means that individual investors, as well as wealth managers, they are interested in finding high performance allocation dynamic strategy to meet the retirement goals or wealth growth objective. So in particular, you can imagine that the employee will have a yearly contribution, I will denote it by Q, into the retirement account at beginning of every year. Then we will need to have an optimal allocation strategies that depend on where the market is, depend on what is the wealth level for the next 30 years, and to try to optimally reach a retirement objective. Okay, so that's the particular application I will focus on, which the problem fits into our dynamic asset allocation problem. Okay, now in addition to the fact that we are looking for control functions at each rebalancing time, this optimization problem is also challenging in the sense that my objective function, it depends on final wealth, even if that objective function itself is simple, could be quadratic, could be piecewise quadratic, or could be some smooth function. Even when the objective function as a function of the wealth itself is smooth and convex, this optimal allocation problem is challenging in the sense that in terms of the control, the objective function is very nonlinear and non-convex. And this is you can easily appreciate that because we look at how our wealth is going to accumulate over time, and the more number of rebalancing time you have, your final wealth will depend on the controls at previous time period more non-linearly. So just in terms of as an optimization problem, looking at objective function, this is not an easy problem to solve because the non-convexity and the increasing non-linearity when you're looking at 30 years or 40 years of time horizon. Okay, so that's one of the challenges, but that's not all the challenging. Okay, so what we have, how are we going to solve this problem from the very beginning? What we have is a single market realization, and that's the maybe of the assets you are interested in investing. For example, the equity index, their return for the last 80, 90 years, right? So what we are given with as a problem we try to solve, we only have a single path of market return that is available to us. So this makes it difficult to approach this problem from if we're going to solve the problem in some kind of learning from data approach, because the amount of data is really, really small we have from the financial market. And this indeed is a typical characteristics of many of the financial machine learning problem if we approach this way, right? We have a very small amount of data for us to learn. And the second challenge is that, well, the problem can be actually become high dimensional, right? So you may think about, just stock and the bond, and you may think about, I would be looking at a different index, different fund as choice of my assets. And if I want to beat a stochastic benchmark, I want to actually form the problem in that way, and the dimensionality of my problem also increase. And if I'm going to solve this long-term horizon, a high-dimensional problem, and there may be even additional information, as some of the research we're currently looking into. The market information could have other market variable we want to incorporate into our decision making. The problem becomes very high-dimensional, and that's also additional challenge, right? And moreover, how do we formulate an objective function, right? Our terminal wealth is a random, variable has a distribution. What kind of objective function should we actually formulate to get attractive allocation strategy? And what about if I'm talking about the individual employee to find the optimal pension allocation trading strategy, there's tax consideration, and there are many other factors. So if I look at this problem, the original problem, directly, we indeed are faced many challenges, and it's a pain to solve it, right? So what's the traditional approach that one we have been using to solve this problem? Indeed, my colleague and I, when we were solving such optimal control problem, this is what we do, right? So we will say, okay, I have the market return realization observations for the last, I don't know, 60 and 80, 90 years, whatever I have, depending on the particular market. So what do? We basically then say, we will assume some stochastic parametric model for the return, market return, right? We could be using jump diffusion model. We could be using regime switching model to try to do our best to model the stochasticity of the financial market, right? And so we get a parametric model, let's say a jump diffusion model or regime switching model. We do a model, we do a parameter estimation, and we get a optimal parametric model that fits into the market realization we observe. Then given this parametric stochastic model, then we try to solve the optimal control problem, right? And because our allocation problem is many period, and it's stochastic, and it's difficult to solve because I have a set of control function at every rebalancing time. And the traditional approach is, okay, I'm going to make the problem easier. I'm going to change this multi-stage, multi-step allocation optimal optimization problem into a single-step optimization problem. And how do I do it? Well, I use dynamic programming principle. I will step backwards in time, one period at a time, to determine the optimal decision at every rebalancing time, right? And so if my colleague is a PDE expert, he would use dynamic programming principle and convert this multi-stage optimal control problem into a HJB equation. And then he will solve it backwards in time and then get optimal allocation strategy. Now, the issue with this approach is that we have the curse of dimensionality. When we do it in this way, we need to compute the optimal strategy at every rebalancing time for every possible market state. And then we have, we have exponential blow up in terms of computational complexity. So this traditional approach, indeed this approach we have been taking for many years, it's difficult, it's painful to do because it requires us to make a stochastic model assumption on the financial market. And it's very unlikely we're going to have, we know how market works, we have a perfect model for it. And so we have error in our model assumption. And then we want to keep the model simple because otherwise we can't solve the stochastic control problem easily, right? And the estimation of the stochastic model itself, it's difficult. We can use maximum likelihood estimation, and suppose we do maximum likelihood estimation of a regime switching model, then that is actually a non-convex optimization problem. And when we are faced with local solution, and that's a difficult problem. Estimation problem itself, it's difficult to perform, right? And then based on this estimated stochastic model, then we solve the stochastic optimal control problem by using dynamic programming. And then we are faced with curse of dimensionality. We can't solve it more than 2 state variables, 3 state variables at most. So this is a traditional approach. It is painful and it is difficult. And so the question is there another way, right? Can we do it in a different way? Can we solve this optimal control problem more easily and robustly? So, so the specific question, so that's what's our objective. So the specific question we ask ourselves is that, okay, our starting point is a single path of market return realization. Is it possible actually for us to take a learning approach from based on the fact that we have only a single sequence observation of the financial market, right? And then given that we are trying to take a learning approach, is it possible for us to do it in a way to avoid curse of dimensionality? And can we do it robustly, right? That's the big thing. We're taking a learning approach. What we want is to perform well in the future, right? Can we do it robustly? And suppose we are able to do it, how does the optimal strategy perform? How does it compare to the benchmark strategy that's currently popular in industry, right? And now if our goal is trying to beat the industry implementation, is there a way for us to actually optimally beat a benchmark from the industry? So those are the questions we have focused on, and that's my presentation will address some of those, most of those issues. Okay, so first of all, if we want to take a learning approach to determine the optimal allocation problem, where does data come from? How are we going to have the data, right? We have only a single realization of the market the assets return, right? So this is all we have, a single realization of, let's say, monthly return from equity market in the last 50 years or 90 years, right? So how do we come up with data that allow us to get to learn from the market, what kind of data can we possibly come up with, and not going to the traditional approach of stochastic model estimation. So what we end up with is to use the stationary block resampling approach, which essentially generates more data path from this single return observation. So how does this approach work? So this is basically a block resampling approach. We will, based on this single market return observation, will randomly sample blocks of random size starting from the random location, okay? And the size of the block, we will assume that it follows a distribution. Okay, a geometric distribution specifically. And for the geometric distribution, we will specify an average block size, right? And I will say more about that as we go on. So then we calculate all those blocks of different size, random size, put them together to generate a data path, return path, which is corresponds to our investment time horizon. Now, the assumption here in order to do this is that we're going to assume that our sequence of market observation is actually circular in the sense that, in other words, after you reach in the last observation, you will go from the beginning to continue sample return, right? So this is the block resampling technique that has been proposed, has been used in financial time series in other contexts. Okay, so this is how we're going to generate our data using block resampling to come up with many more paths of market scenarios, right? So, okay. So, okay, we're going to use the block resampling to generate data, generate training data to learn our optimal strategy, right? So there's some arguments that supporting that to learn the strategy using this technique is reasonable. Well, essentially what we're doing is that, okay, we think about, we have this one path of market return realization. So our market scenario, that's our augmented market scenario, essentially you can think of it as, I have market running session of random length and randomly permuted and concatenate them together. So in some way, it is come from the market and different lengths of time period, and also so there's some I guess rationale one would think this is a reasonable approach. Well, so okay, that's fine. So that's our approach to generate our data to train our optimal allocation strategy. But what about testing data? We're doing machine learning approach, a learning approach to determine our allocation strategy. We have to make sure our strategy really perform out of sample, out of the training data set, right? So the question is, how do we generate testing data? Well, in typical machine learning, the assumption is that the training data and the testing data, they are samples from the same distribution, right? We just require our testing data have not appeared in our training data set. Our testing data instance are out of the training data set. So it's out of sample of training, but they come from the same distribution, right? So that's how we typically handle the training and testing in machine learning, okay? Now, so here we start from a sequence of market return scenario, that's observation. Now we did the block resampling, come up with 10,000, 100,000 of the market scenario corresponding to my investment horizon. We specify some expected block size to do this, okay? So how do I come up with testing data set? Well, if we say the expected block size, we use the same block resampling technique to generate testing data set. If we assume that expected block size is the same as the training data set, then our argument is that essentially you are performing out of sample test. So if you use the same expected block size as your training data generation, you are performing out of sample test. And I'll give you some mathematical rationale to support that. Now, suppose I can actually, in this using this technique, I can even generate more stringent test, if you like. And when I use a different expected block size to generate, to block sample, to generate my testing data set, then the distribution of my testing data set is actually different from my training data set. And so I am, in that sense, I'm actually performing out of sample distribution. No, I'm performing out of distribution test. And so that's something we will do as well. And then one might be still concerned because while you're doing your training and testing based on a single pass of a return observation from 1926 to 2015. I mean, your training and testing still come block sample of this whole thing. And are you somehow look ahead and is that reasonable? Are you really testing it? So then one can do further say, all right, I can really split my historical market observation into non-overlapping segments and generate training data from one segment and testing block sample from a different segments. And in that case, then really it's really different, and then I think it's hard to criticize that. So we actually perform all those different kinds of tests, right? And furthermore, I mean, one could, because we've been doing computational finance for so long, we can also we know how to estimate the parametric model. We can also do parametric model estimation just as additional testing, sanity checking, and generate scenarios from our stochastic parametric model for additional assessment if we still not so sure if the whole thing really works in a robust fashion. All right, so we actually in our computation we will perform all of that. Okay, so what I want to just kind of provide some kind of support that this framework we are conducting in learning and training is mathematically sound, right? So what I wanted to trying to answer, the question I'm trying to answer is that when we use block resampling, it actually doesn't lead to a solid out of sample testing. And so what is this theorem here we're trying to say? So essentially what this theorem says, okay, if I have a n total number of observation, my market realization, I'm going to do block resampling of this market realization single path. I'm going to do block sampling from this observation. Suppose I want to generate 2 paths of n data return, n data points, right? So, and path 1 is generated using expected block size of B1 hat, and path 2 is generated using the expected block size of B2. Then the probability of these 2 paths being identical is given by this expression here. Well, this looks very complicated. What is the upshot of that? Okay, so here's basically a sort of a numerical example to give us some comfort or assurance that supporting my statement that this technique does need to sound training and testing. Okay, so if I say I have 19 years of return observation, monthly return observation from the market, I need 30 years of monthly return to look at my investment horizon. If I use the expected block size of 2 years for training for 2 paths, sampled from 2 paths with the same expected block size, and if I have a training set of 100 return paths and testing set of 10,000 returning paths, and then the probability there exists a training path and testing path being actually equal is less than 10 to the power minus 29. So this basically kind of assure us, yeah, this framework is a reasonable approach for us to answer the question of how do we generate testing data using the block resampling. Okay, so, all right, so that's how I'm going to generate data for my learning approach for the optimal allocation problem. Okay, now let me move on to talk about how do we solve the learning problem. Remember, our original stochastic dynamic optimal control problem is a multi-stage optimal control problem, right? And we don't want to use dynamic programming principle to convert this problem into a sequence of optimization problem by solving backwards in time, because that leads to curse of dimensionality. So what we want is that we want to see if we can actually solve the optimal control problem, the original optimal control problem, directly in a single optimization. Okay, suppose I already have my many market scenario that come from my block resampling. So I have a, let's say L or 10,000, 100,000 of return scenario, market scenario. That's given to me by block resampling. Okay, corresponds to my original optimal allocation problem. Then what I have is this scenario optimization problem, right? So I have control at every rebalancing time corresponds to different scenario, every scenario, and subject to the constraint that I have look at percentage allocation, it's a constraint between 0 and 1, they have to sum to 1. Okay, and then I have a different, I have many scenarios of the terminal wealth based on my calculation. Okay, so the original infinite dimensional stochastic control problem, when we use the training data set, it becomes this finite dimensional scenario, a finite dimensional scenario optimization problem. Well, we can try to solve this, but this is going to be hard because the number of optimization variable will be proportional to number of assets, number of rebalancing time, and the number of scenario I have. So this is a huge optimization problem, right? So yeah, and in addition, I solve this scenario optimization problem. I'm going to apply it to in practice to have an allocation strategy. Well, this only gives me the optimal control corresponds to the scenario. But what I need is really a optimal control model tell me at every rebalancing time how do I allocate my strategy. So this is it's still not easy to deal with the scenario optimization. Even though it's finite dimensional, it's still hard to for us to work out. Okay, so what do I do? Of course, everybody think, well, let's do a machine learning approach, right? Okay, what we want is the optimal control at all those n rebalancing time, right? So the idea we apply is that I'm going to assume the optimal control is a function of some features, okay? And so the optimal control will be a function of feature at a particular rebalancing time, right? The feature or the state variable for my optimal control will be in this pension allocation problem, could be the wealth of my strategy at this time point, and as well as how much time left to go. Or could it be other market variables like realized volatility or volatility index or whatnot you can come up with, or could be trading signal from moving average and so forth, right? So the main idea is that I'm going to represent the optimal control for every rebalancing time using a single control function, where the feature will reflect market the state variable for my control, as well as how much where I am, how much time is left, right? So if I do this representation, then my control function will be somewhat parameterized by a set of parameters like the weights of neural network, right? And then my scenario optimization problem now becomes this. I have my objective function depends on the final wealth, terminal wealth. I have the control, and then I'm determining this non-parametric neural network, which will give me the control I need for every rebalancing time. And then unknown of my optimization problem is the weights of neural network, or the parameter of my control function. So I'm making progress, right? Instead of my scenario optimization problem involving a lot, number of decision variable depends on number of scenario, rebalancing time, assets, and so forth. Now my optimization decision variable for my optimization is a parameter of my neural network. It's the parameter of my control function, which I will model it unparametrically. So that's good. I hopefully I have reduced the dimension of my optimization problem, but I still have other issue because my optimization problem is controlled, right? My control is still for every scenario at every rebalancing time, right? So I still have order m times n times l number of constraints, and solving such optimization problem is just as hard as when you have the number of decision variable being that large. So that still doesn't work. So what do I do? Well, okay, so we're going to use a neural network to represent optimal control. I'm going to handle the constraints in some suitable fashion on next slide. And it turns out that our optimal control for the dynamic allocation problem, at least for the pension allocation problem, and perhaps can be generalized to many different problem contexts, a very simple neural network is sufficient, okay? And for the pension allocation problem, what are we going to use? What do we end up using? It's just this baby neural network. It cannot be simpler. I have features. Think about the wealth I have so far at this time, at the rebalancing time, and how much time to go. Those are my two input features. I have one hidden layer. It's just 3 hidden variables. It cannot be smaller. And then my output is P1 and P2 tell me the percentage allocation in stock and bond, for example. Right? It's a very simple neural network. And my optimization problem in terms of number of optimization variable is just number of those arrows connecting all of them. It's just a number of weights, right? All right, so that's my neural network control model. Okay, what do I do about the constraints. How do you handle this large number of constraints? Well, it turns out that we can actually, at least in this case, handle it fairly easily. What we do is we choose the activation function for the output layer carefully. Yeah, if we just use logistic sigmoid activation function, and so the output function is a function of the output of neural network is a function, this sigmoid function of the hidden layer variable, right, in this way. So we automatically satisfy the bound constraint between 0 and 1 and sum to 1 constraints. All right. So the input feature, as I meant, to the input for the hidden layer, as I mentioned, is wealth level at rebalancing time and time to go, and we use a simple activation function that is written here as well. So in other words, we have a simple neural network model for our control, and by choosing activation function carefully, we were able to actually change the problem into a unconstrained optimization problem, right? So, okay, now my training optimization problem then is basically this finite dimension optimization problem, right? My objective function depends on the wealth. The wealth is calculated explicitly by this formula from the feature variable hidden layer weights, and the weight of neural network. And so I have an unconstrained optimization to train my optimal control. And the number of weights in this case is very, very small, right? It's 2 times 3, whatever. This is right here, right? Number of features, number of hidden nodes, and number of assets. Right? It's a very small optimization problem in terms of the decision variable, right? So yeah, so by using this approach, right, we actually simplify the problem significantly. The original scenario optimization problem has constraint, and number of variables is proportional to, is right here, order mn times L, proportional number of scenarios, and number of constraints is also same magnitude. And then my neural network training optimization problem in terms of number of variables is very small, right? This is a number of variables of far, far smaller than scenario optimization problem. And in terms of, if I solve this small optimization problem, right, I will need to evaluate the objective function, compute the gradient, and compute the hashing of objective function if I want to do that, and which actually in this computation we do because the dimensional problem, because the neural network is so simple, right? So in terms of gradient and hashing calculation, second order derivative calculation, it does scale linearly with number of scenarios, right? It depends on neural network structure, quadratically if you're going to use the hashing, right? So in our computation, because what we have is like a problem, our learning problem is so small in terms of optimization variable, we actually use second order method to solve it. And the reason we do this, well, I mean, you can solve it using stochastic gradient or first order method, but the reason we choose this, there are a couple of reasons. One is that the method is more robust because it's second order method, and furthermore, there's no issue of choosing the learning rate, right? I always find that the stochastic gradient, how do you choose learning rate? You know, it depends on what you choose. Then you don't. So the second order method is feasible in this financial stochastic optical control problem context, and why not? We have a way to formulate the problem, we can solve it, right? So that is what we're going to do. We use actually a trust region method, second order method to solve it. And when the problem becomes larger, I mean, it depends on the context, how you're doing it. I mean, stochastic gradient is a possibility, and some of my students have been using it. One of the tricky issues is the choice of the learning rate, which it's challenging if it goes to first order method. In any case, so our training optimization problem is easier, less painful, hopefully, to solve it. And all right, so that's my learning problem. Okay, so let me move on to the next component of a presentation. That is okay, what objective function should I choose? That of course is problem dependent. And if I'm looking at the pension allocation problem, right, a first objective function that I can think of is, well, when I retire, I want to have $2 million or $3 million, depending on how you're comfortable living comfortableness, right? So I can say, all right, I really want at the end of the investment horizon, I want to a wealth level W star. So I can specify a wealth target. And then a reasonable objective function is to minimize expected quadratic shortfall. I want to reach that wealth level as best as I can. I want to, and I minimize the quadratic shortfall, and that will make me focus on really not to fall short. That's essentially the quadratic shortfall would bring you. And it turns out if you use this quadratic shortfall objective, the strategy is also actually, if you solve it, use this objective, it corresponds to mean variance optimization problem with a fixed risk version parameter as well. I don't have to go there for this presentation. All right, so okay, so that is the first objective function we can consider in the context of pension allocation problem. When I retire, I want to do my best for my strategy to reach that wealth level. All right, so okay, all right, so sure, we will use that objective function. Okay. Then how do I assess if the resulting optimal strategy really is attractive? Well, one way for me to do this assessment is compared to benchmark in industry, right? So one of the very popular allocation strategy in wealth management, in pension fund management is a constant proportion allocation, right? So we're going to use this couch potato constant allocation as a benchmark for my assessment, right? So then the immediately, okay, it says, well, if you really want to beat the benchmark, then why don't you actually use your optimization and mathematics and computation to do it, right? So then the next question is, okay, how do I actually optimally beat a benchmark, 50%, 50% allocation strategy? What kind of optimization problem can we formulate? All right, so we want to also consider optimal strategy corresponds to beat the benchmark. And the objective function we end up choose is this asymmetric objective function. Let me try to explain what is this objective function. Okay, so we basically, we want to beat the benchmark. So we elevate slightly our benchmark terminal wealth. So you can think of this exponential, this continuous compounding kind of growth rate. We call it a spread of S, right? To elevate my terminal wealth. And then what I do is I'm going to minimize my quadratic shortfall of the benchmark, right? But I'm also going to maximize of my outperformance of the benchmark. But I don't do it symmetrically. I'm going to have a quadratic shortfall and a linear outperformance. And we choose this because really, I mean, our strategy will generate a terminal wealth distribution, right? And it's difficult to describe what is the attractive strategy by a single objective function, right? And so objective function really, the objective function is doing is really trying to somehow formulate or trying to characterize the distribution of the terminal wealth we would like to have. And so basically, and that is to shape your distribution using objective function, that is a hard problem by itself. But what we did is basically saying we like the risk, we don't like the risk more than we like the outperformance, and we will end up with the stochastic benchmark outperformance objective, right? And when we look at this stochastic target outperforming optimal control problem, excuse me, then I just want to point out that the dimension of the problem increase, because now the wealth of my benchmark strategy at rebalancing time become a state variable for my optimal control. So the dimension problem also increases, as I mentioned before. All right, so that's a different objective, and those are the two objective functions we're going to use to hopefully determine a optimal allocation strategy that is attractive and perform well. Okay, so this is this concludes my sort of mathematical description or my modeling and the computation aspect of the computation of the approach, right? So what I would want to move into is talk about how well does this work? Those objective function, those computational framework, and those data augmentation, do they work, right? Will they perform well in practice? So we do this assessment. We look at US historical market data from 1926 to 2015 in this presentation. That's the data we have, and from CRISP. And so in my presentation, I'm going to consider the following allocation optimal control problem. I'm going to consider two asset allocation, which involve cap-weighted CRISP index and a 3-month treasury bill. And I'm going to consider different two asset allocation just to as a different performance assessment of using equal weighted index and 10-year treasury. And we will also consider 3 asset allocation problem involve one of the index, 3 months, and 10-year treasury bills and treasuries. And of course, we will also consider beating the benchmark problem as well. Okay, so in the computational results, we use the bootstrap block resampling of the market data observation to generate our training data as well as our testing data. I'm going to also consider the situation where the data comes from a parametric model, specifically jump diffusion model assumption, and where we actually estimated the optimally and the best possibly the jump diffusion model that described the market, single market, same market scenario. And the reason we do this is because I'm going to use this experiment to show the accuracy of our proposed framework in learn the optimal strategy. Okay, all right, so those are the data. Okay, all right, so the first results here is basically a accuracy assessment against the ground truth. So when we started this research at the beginning, I was doing optimization, machine learning. Peter, my colleague Peter, he's doing HJB equation. He said, there's no way you can use a machine learning approach to learn the optimal control strategy in this setting. And so I said, well, try me. And so, okay, I said, okay, I'm going to do this. And then I'm going to just use 10,000 scenario from simulation of the jump diffusion model. I will learn the optimal strategy. I'm going to compare to the corresponding optimal solution that's computed from solving HJB equation, right? So this table basically is a comparison to show that actually with our very simple neural network, we are able to get very accurate solution when we compare to the true solution, the grounded truth, right? So the optimal, the neural network learned strategy. So we learned from 10,000 scenario. This performance, the statistics right here is collected by using 160,000 Monte Carlo simulation of the same parametric model. So you can think of my test model if you want. So this is a two asset allocation problem. We use the cap-weighted index, right? So the key thing is here I want to point out is that if we compare the neural network strategy with the ground truth strategy, you see the expected wealth here is exactly the same. Actually, we choose the wealth target so that the expected wealth from the two strategy actually will be the same, which is the same as a constant proportion average wealth. So we put them all the same. We can do this by just changing our target. I think this, I might have had a typo here. The target is probably different from CMO 5. It's a bit higher. So the all strategy will have the same expected wealth. Okay. Now let me compare the neural network strategy and the grounded truth in terms of standard deviation. They are very close, and the median of the terminal wealth is very close, and the probability of falling short on a few wealth level, 500, 600, they are very close. Right? They are essentially, it's sufficiently close to the exact solution. The difference comes from that the strategy is computed using 10,000 simulations of the same stochastic model, right? All right, so that's first one thing is the accuracy assessment. We say indeed compared to the exact solution, numerical exact solution, and the learned strategy perform just very similarly. Now, if we compare this to constant proportion strategy, where we allocate 50% to equity index and 50% to bond, we see that while the optimal strategy from stochastic optimal strategy has much smaller standard deviation of terminal wealth, much higher median wealth, and the probability of falling short of the wealth level 500, 600, and the wealth target, the optimal strategy, it's just significantly better, right? So that's basically the first, the results I would like to describe. All right, so that table here basically compare strategy based on a few statistics, right? A few quantile, right? So what about if I look at, I want to have better picture, more complete picture. Well, to do that, we can look at CDF, right? So here, this plot here, we basically plot the probability of terminal wealth less than a wealth level. So the horizontal axis is the wealth level, and the vertical axis is probability of falling short on that wealth level. And so here are the what I want to draw your attention to. So the green CDF here corresponds to optimal control, computed from neural network learning approach. The red one corresponds to the grounded truth, computed from HGB equation. And you see these two CDF nearly coincide, right? There is a bit of difference. That's because, as I said, neural network control is learned from 10,000 scenario of the stochastic model, right? And so that's first comforting observation. Now we compare it to the constant proportion strategy. The blue curve here is CDF of a constant proportion strategy. And we see that, so because our objective function is trying to reach the wealth level, which is somewhere 700 something here, right? So we see that, of course, our objective function ignores wealth above it. I don't try to achieve there, right? I want to achieve this wealth level as much as possible, right? And it's able to do that, right? So relative to the blue line of constant proportion CDF, the optimal strategy is lower in this entire segment of the wealth. The shortfall of the wealth below that, terminal wealth below this wealth level in this segment is significantly smaller for the optimal control solution compared to the 50% strategy. And of course, on the very extreme left tail, there is a small probability of the constant proportion strategy actually is slightly better, right? But this is what objective function, quadratic objective shortfall can achieve, and indeed it does a pretty good job for a large horizon of a wealth level achieve above that. Okay, so the left plot is for cap-weighted to asset allocation. The right plot is similar, except it's for equal weighted and 10-year treasury to asset allocation. So the picture is roughly, it's qualitatively similar. Okay. All right, so that's essentially the comparison in the two asset case against the grounded truth and constant proportion strategy in different perspective of a few statistics and the entire CDF. Okay, all right, so what about the robustness of the strategy? As I mentioned, we perform both out of sample test as well as out of distribution test for the optimal strategy. So this table basically shows that so we learned optimal strategy using an expected block size of a half year to generate our training data. And then we will, here, the first top panel here, report then the performance of our training with the expected block size of half a year, right? And compared to the constant proportion strategy. Oops, this is a 3 asset case. I had a table for 2 asset case before, but I think I deleted it. Okay, so this is basically a robust test results for the 3 assets case. Okay, we have a cap weighted index, 3 months treasury bill, 10-year treasury. Okay, the first sub panel here is the training performance with the expected block size of half year. Okay, then the next panel here, reporting out of distribution test results of expected block size of 1 year. The testing data set is generated with different block size. And you can see that, first of all, the optimal strategy is performing better than the constant proportion strategy, which is 60%, 10%, 30% allocation, I should say. And then we have out of distribution tests for different expected size, 2 year, 5 year, 6 year, and 10 year. And the important point I want to make is that, first of all, across different out of distribution tests, the comparison between the 2 strategies are qualitatively similar. So, so that's a robustness test for the 3 assets case. Okay, so I have a few more computational results slides. So now I move on to talk about optimal strategy that's determined by formulated problem to really optimally beat the stochastic target. Okay, so I'm going to use 50-50% as my benchmark to beat. I'm going to put this elevated target to be slightly higher, basically 1% spread yearly, right? I'm going to solve the stochastic target optimal strategy training problem using training data with expected block size for half year. And I'll also do out of sample testing using the same expected block size. Okay, so here the plot is a histogram, different way of looking at distribution of the terminal wealth. The blue one comes from the optimal neural network strategy, and this pinkish one is the distribution of the wealth from 50% allocation. Okay, this is training on the left histogram, and on the right is out of sample testing histogram performance. Okay, so what I want to point out is that, well, our optimal target outperforming strategy has a terminal wealth significantly more right skewed. So because we are trying to beat the market, there's a higher probability, the right tail, higher probability of achieving higher wealth. And so then one would imagine that, well, you probably take more risky strategy, then you're going to give a lot on the left tail. But if you look at the left tail here, you see that there's only a slight underperformance over the benchmark strategy in the probability of those very of the extreme wealth level, right? So I think overall, from the whole entire distribution perspective, the optimal strategy does seem to be much more attractive on that benchmark strategy. And another point I want to make is that the testing histogram looks just almost the same as the training histogram. This is out of sample testing, right? And we have plotted out of distribution testing using different block size, and in terms of the distribution comparison between the two, it's qualitatively similar. So in the paper, we'll have more plots. All right, so this is one picture of our optimal stochastic outperforming strategy. So what is this strategy? What it's doing? What does the strategy look like? So here the plot here is trying to convey some sense of what the strategy look like. So this is the vertical axis show the percentage allocation to the risky asset. And in this case, I think it's the CAP index, right? So, and the horizontal axis is time, right? It's 30-year time horizon. Okay, so what this model gave me, what this plot is trying to show is that we show the average allocation in risk asset allocation over time, right? So this is the mean allocation, and this green line is the mean allocation. And what we can observe is that the allocation starts from initially very risk taking, and over time it gradually become taking less risk. And that's the mean, and this is the median allocation in the risky asset. That red line is median allocation. And we also plot the 55th percentile and 95th percentile in the risky asset allocation, and they all tend to be decreasing over time when you're taking less risk as you move towards your retirement time, right? And moreover, this 5% allocation seems to decrease more quickly over time. Okay, so that gives me some idea of what this strategy look like. Okay, so I'm going to have two more pictures. So remember, we generate training data from historical past by block resampling, right? Then we generate many scenarios using the block resampling, right? So the question is, how does this optimal strategy perform on the historical past itself? And now, based on the mathematical analysis I showed before, well, actually the historical past itself, it's not in the training set, right? The probability is in there, it's very small. And indeed here, we plotted that the black path is the historical path of the wealth for the correspond to constant proportion allocation. The blue path would be the closest path in my training set to the historical path. And the closest is being measured by Euclidean distance of the different time points in the investment horizon. So indeed, the training path, the historical path is not in the training set. And this is what the closest path look like in relation to the historical path, right? So I want to look at, in the historical path itself, right? Suppose the market going next 30 years, really just repeat the historical path again. What would the strategy look like, right? So here, this plot basically tells me what the strategy look like, how it will perform. So first of all, on the vertical axis on the left, it's the wealth. This is for, I guess I should have mentioned before, our computational setting is a cash injection of $10 each year at the beginning of each year, right? So here's basically on the historical path, constant proportion is the red wealth path for the optimal strategy. Oh, no, sorry. Okay, let me start again. The red path is the performance of the wealth. It's the wealth of the constant proportion strategy. The blue path is the wealth of optimal stochastic outperforming strategy. The black curve, its vertical axis is on the right. It shows the allocation to the risky assets. Okay, so what's the point I want to make here? Well, on the historical path, the optimal strategy is turned out to be always above the benchmark strategy in wealth level, right? So that's one point I want to make. And then if I look at the allocation strategy on this particular path, you can see that it starts with around 86%, and then it went way down, okay? And so basically, when the wealth level market performed well, wealth becomes really high, the risky asset allocation went way down. And when the wealth went down, asset allocation goes up. So essentially this picture here shows two things. One is that optimal benchmark strategy is performing well on this particular out of sample historical path. Secondly, the strategy is contrary strategy. When the market will outperform, it goes down. When it goes down, it goes up. And when you get close to the investment horizon, it de-risks, the allocation becomes much smaller. All right, so that is the behavior of the strategy. I think I've talked about, touched upon all the points I wanted to make. So in summary, basically in this research, we consider a framework to look at optimal allocation problem, particular in the context of long time horizon allocation. And what we want to be able to do is to obtain this optimal strategy with more ease, more easily, and ensure the strategy actually perform well in practice as well. And this problem is by no means easy. It's difficult both from modeling perspective and the computational perspective. And the way we approach this problem is by using a learning direct from the data approach, not making any assumptions. And in particular, we augment market data single return path using block resampling technique. And we look at this learning framework in terms of training data generation and testing data generation. And we provide some kind of mathematical assurance in the sense that using this approach, we are indeed performing out of sample testing and out of distribution testing as well, right? And we also look at the performance of the strategy, look at a particular historical path to show that indeed the strategy performs well. So in addition to the modeling aspect of data augmentation, we also look at how to solve the optimal control problem, and which is a difficult problem. And the way we approach it is basically using a learning, non-parametric learning approach to determine the optimal control problem strategy directly by solving a single optimization problem. And the way we do this is by representing the control at every rebalancing time with a single control function, and the control function is a function of state variable at rebalancing time and time to go. And we demonstrate that this computation, first of all, is able to achieve good accuracy because we compare to when it's low dimensional case, 2-axis case, we compare to the ground truth. We look at the different statistics and look at the CDF to say that indeed two strategy looks very much the same, and assure us the accuracy can be achieved. And we also talk about the computationally, it's much more efficiently to solve the problem in this proposed fashion, right? And we designed objective function for different in the pension retirement allocation problem with different kind of consideration to design the objective function to achieve that objective, right? One is to try to reach a wealth target at retirement with a minimum probability of shortfalling. And then secondly, if I'm going to persuade industry that this is a good strategy, we can try to actually optimally beat the benchmark by formulate appropriate objective function and formulate a learning problem. And based on historical market data, we show that indeed the optimal strategy obtained in this framework consistently outperform constant proportion benchmark strategy, and robust testing looks good. And also the optimal strategy, both in the constant wealth level target case and stochastic target case, is essentially a contrarian strategy. When market goes up, it allocates less risky assets and reverse. And moreover, the allocation strategy decrease over time. As you get close to retirement age, you are exposed less in the risky assets. And we believe that this framework of solving the optimal control problem, decision problem, trading problem can be applied to many different financial decision problem. And we're currently working on looking at what happens if we have to consider personal tax, and also what about we have additional thing to consider, the market signal, the factor, and so forth. With that, I hope I have not, hope my timing is okay, and I'm ready to answer any questions.
Thank you very much, Yuying, for this nice overview and this nice and detailed presentation. There have been several questions on the chat, and there's a lively discussion with questions and already intermediate answers. So I see a first question was from Shashi. He said, are we assuming for bootstrapping that the return process is stationary? For instance, I feel volatility clustering in the bootstrapped path might not hold.
Yes, so that's a very interesting question, right? So this is a block bootstrapping. And that is the reason this is the block bootstrapping is used. It's in recognition that there could be serial correlation in the time series. So if you choose the block size to be very, very small, like just 1 month, right? You essentially are saying, I'm going to generate that, ignore any serial correlation. So by varying the expected block size, you will be able to capture some serial correlation. Does that answer the question? I think that's essentially what he's asking. So we're not assuming this is non-parametric way of sampling, of generating data from time series. It will be able to capture some degree of serial correlation. But of course, one issue is how do you choose the expected block size appropriately that is actually consistent with your degree of serial correlation, if you like, of historical past, right? So that is a tricky question, but what we've done here is basically, so at least in the context of this pension allocation, we've done different block size, and of course, when you do different block size, distribution change in the sense that the serial correlation degree of serial correlation captures changes, right? But what we want to emphasize there is robustness, and in particular, with the perspective of a relative comparison between constant benchmark strategy to the optimal strategy. I hope that answers that question.
Yes. I see in the chat this answers your question, he says. Paul Kerber, you want to ask it your question yourself, Paul? Because there are several questions.
Should I talk or?
Yes, yeah, go ahead, yes.
It's a bit related to this volatility clustering question. So if you patch the blocks, don't you have some artifact where it goes from one regime to the other if it's taken from time periods where there was a different volatility regime? Or, I mean, doesn't it make some artifacts when you patch the blocks together?
Yeah, it indeed. I mean, the thing is, you start with a single path observation, right? And we have to come up with a reasonable market scenario to determine optimal allocation strategy by considering everything that is reasonable. Now, the block resampling technique is essentially a way of non-parametrically generate market scenario but it requires the choice of the expected block size. And I agree that if you choose differently, you can destroy or you are not able to capture some of the effect in volatility clustering. And so then in some way, then the decision becomes, how do you choose the expected block size? But I think that is an important question, and I don't think I have all the answer to that. And I think it's a question actually worth to think about and further research. But what I've shown that is in this context of a long-term horizon allocation problem, right? It seems to be that expected block size choice, it's not as problematic in the sense that if we choose 1 year, 2 year, the strategy does not, the optimal strategy does not change significantly. So that's the degree I can answer your question. Yeah.
Thank you. And Paul, there was another question from your side, so feel free to ask that one as well.
I was wondering how relevant very old data is. You're talking about the 1920s, or
yeah,
because I mean the markets were very different then.
Right. So that's a very good question. Okay, so we have a single path, right? And we are trying to determine optimal allocation strategy going next 30 years forward, right? So the question is, how do we describe or represent that randomness into the future? The block resampling technique, my argument is that it's essentially look at what has happened in the market in the last 80 years, whatever. And it is basically that I take a random length of market running session, right? And randomly concatenate them together. And I've considered all different kinds of scenario. So that becomes, so of course, the optimal strategy is not determined based on a single path, right? It's not, the optimization problem is not based on a single path. It's based on all the different scenarios generated in the sense of I can have a historical market session running at different lengths of time, regime, different time, and different, starting from different point, different lengths. So that's so I'm training a strategy by consider essentially in some way all the possible scenario I can come up with based on that single path, right? But the issue really is then the expected block size I still have to determine. But so your question about, are you determining the strategy based on single path? My answer is not really, right? My training data set has 10,000 scenarios, come from random permutation, random size of a session of the historical market. So and indeed, you will see in my training data set, if you plot it, you will see scenarios come from all different way. So yeah, you can have very different scenarios. So it's not based on a single historical path. It's not just a single historical path, but rather it's considered possible scenario based on this observation. What is a reasonable way of coming up with the scenario?
All right. Martin asks, did you compare with the optimal constant allocation? In the historical comparison, the neural network might outperform because it takes more risk.
Sorry, so compared to, I'm not so sure if I get the question right. You mean the constant proportion?
With the optimal constant allocation?
Oh, you mean optimal? Yeah, we actually did that. The optimal constant strategy doesn't perform very different. It's deterministic, right? So it's basically, you are saying the allocation percentage is determined, the constant is determined by some optimization. We actually did that, but the performance of that strategy is not, it's not very different from a reasonable constant proportion strategy. So we did consider that. I don't have the plot here, yeah, but that does not change the comparison between a fixed proportion constant proportion strategy with the optimal strategy.
All right. There's a question from Edouard. Does the wealth level depend on inflation? If the benchmark strategy just
Yeah, good point.
produce a much higher wealth than the target value, it will underperform, will it not?
Yes. That is a very good question. So if you bring inflation into the picture, you have another random factor, right? So we are currently actually looking at this pension allocation problem under tax, and in which we actually consider the inflation factors in there as well. So those are right. There are many additional things one could consider putting into this framework to answer to get to the strategy. So I think the main point of this research is really to show that yeah, we can come up with different way of looking at this optimal control problem, and we can get a good accurate result if in terms of solution approach we can solve high dimensional problem, but you know, depends on how much factor you take into consideration, this framework will allow you to address many of those issues, and those are important. Yeah.
And then he also asked, what about a buy and hold strategy for 30 years as a benchmark?
Buy and hold, I'm sure at some point we looked at that, but I mean, buy and hold is basically 100%. Oh no, it's yeah. Well, I mean, buy and hold, you don't have rebalancing. I'm not so sure. I almost think that at some point we looked into that too, but I don't. My belief is that strategy doesn't play a role, but I should double check before I say that. Yeah, I think the industry strategy is a couch potato strategy, as a constant proportion strategy, most popular ones. Yeah, that's we compared with. Yeah.
I see a question from Chris. Chris says, let me see. Sorry, I missed it maybe on slide 26. But is there an intuitive explanation for median deviating from the trend of mean initially in the shape of the distribution of outcomes?
That's a good question. Is there intuition? Yeah, that's a good observation. I haven't thought about that. I don't have a quick answer to you, so I will think about that, and I maybe and possibly discuss with my colleagues if they have some. Hey, is Peter there? I'm not so sure if Peter is there. If he's there, he can jump in. The answer is no. I don't have a quick answer. So, but it's an interesting observation. Yeah.
And then I see Eduard asking, could we use the upside values of the wealth to buy the guarantee, a put option from a third party? The third party will hedge it dynamically. We could implement the dynamic hedge strategy ourselves without buying from a third party, at least for the two asset case.
Okay, so we have not considered that. We maybe consider, well, but it's a very interesting question because one of the something related to your question, maybe I can comment on. So one of the co-author, Ray, is from the asset allocation fund from Nürnberger, and they are very much interested in looking at a put strategy and in combination with trend following strategy. So we did do some work of looking at a combination of put strategy and a trend following strategy in some way, but maybe not specific as what you're asking is to put you want to consider the put strategy as well as the risky asset, all in combination, all of them as an asset allocation problem. We probably did some version of that, yeah. Yeah.
Okay. Carlos asks, how do you expect the neural network technique to scale with the dimensionality? Suppose you add inflation or any other factor in.
Right. So let me see if I can go back here. Yeah, so currently we have a postdoc and a PhD student. We are working on higher dimensional problems involving other factors. So the neural network training optimization, right? So as you have more feature variables, that is my D here. So essentially, it's linear with respect to the number of features. right? They scale up linearly with the number of features. Yeah, so if you just do gradient descent, if you do Hessian descent, it will scale quadratically with the number of features. So there are a few ways that computational cost can grow. One is number of assets, number of features. So they scale up linearly or quadratically.
All right, thank you very much. I think that concludes all the questions for you, Yuying. So thank you very much for answering them, and thank you very much for your presentation.